went through everything except your last two. So make sure you can do this. This one, I'm not sure if the book made a mistake, because normally you won't see this off, and see if you can see why I think they made a mistake. The consumer group claims that the mean annual consumption of cheddar cheese by a person in the United States population is at most 10.3 pounds. Annual, 10.3 pounds, at most. Question, Eric?
Well, actually, just look at it.
Okay, and then you saw a problem? Less than or equal to. That's our HO. It has the equal sign in it. Our HA, therefore, is a greater than. They pulled out all the information. We're going to see if we can reject this claim. So therefore, we know the claim must be an HO. Yes, Nick?
Is it, the H is pointing to the right, so it's right tail.
So it's right tail.
One minus.
Well, here's the problem. So see if you saw a problem with this. Okay, so yeah. So let's take a look at this. You do your Z-score. Your Z-score, boys, came out to be negative 1.9. But where is the tail test? To the right. So why is this different than what we've been doing? Well, it came out negative. Our right tail test should have been up here. It should have been here where the right tail is, right? So either it's two things. And you still have to find your area to the right, which is why we had to subtract it from 1, because we couldn't do you could do the positive 1.9 and get the same answer. But we had to subtract it from 1 because we want the area to the right. It could be one of two things. The book might have meant at least instead of at most, and it's backwards. Or this sample may not be the greatest of samples to test this with. So the person who's evaluating this may look at this and say, well, it kind of doesn't fit what I thought it would fit. Maybe it's my sample. Maybe my sample is off. So maybe I might want to do this again before I actually throw this sample out. Maybe this is the way it's going to be. Or maybe this was as extreme of a case that you can get. So we're going to fail to reject because it's not even close. Look at your p-value compared to your level of significance.
Even if it was messed up like that, so you use that one instead of...
You have to use what you're getting. So that's why maybe when you look at this and you fail to reject HO, that's a statement that you're going to have to take. So
I'm just confused because even if you look up negative 1.9, you don't get 9.1.
no, you don't. You get the area here. But what area do you want? You want the area to the right. So that's what I'm saying. It's kind of backwards on how they did this.
We're going to have more like this?
Well, it kind of makes you think. It's a claim that you challenge. It's a claim made by a consumer group. You challenge this with your test data. Did your test data be able to prove that claim wrong? Could you say it was wrong? From this, we had to fail to reject it. So no, we're saying it has to be good. Now, if I'm a person testing this, I might say, did I do this randomly? Or am I so far off in what I thought it would be? I'm thinking it's going to be more than 10.3. Maybe my assumption is wrong. Maybe my assumption is wrong, or maybe my sample wasn't a good representation of people that eat cheddar cheese. You know, maybe I got all these people that love cheddar cheese. You know, maybe I got the wrong, even though I sampled randomly, and a sample size of 100 is a pretty nice sample size. So maybe I want to do the sample again and test again before I throw it out. Did you see where we're coming from here? From the left, from the right? Did this fit your pattern? No? No. Nick noticed it. Aaron, what did you notice?
I thought we were supposed to go to the other side, and, like you go to the negative and you swap to the other side if that number's too high.
Okay, say that again.
If the area is too high, I thought you were supposed to switch to the opposite.
Okay, and yes, in a normal situation, yes, because normally doesn't your right tail test come up here, and doesn't your Z-score come out positive? But we found one that didn't fit the norm. It didn't fit what we expected to find. When you can't dispute how you solve this, you have to still use your formulas. You have to still solve this. But like Nick said, and he did this, shouldn't it be this little small area? No. God bless you. It should be greater than. But I'm finding this little small area. I'm finding my negative z-score. Didn't I expect a positive z-score? According to, wouldn't you think, a right-tail test? Didn't some of you say right-tail test? Positive z-score? So a couple of things could have happened. It could have been mistyped. It could have been maybe a wrong typing. Maybe they meant to say more than. Maybe this was a more than and not a less than or equal to at most. Or maybe when I challenged this, I didn't make a good sample. My sample wasn't valid. Or maybe I really didn't have a good challenge. Maybe really they do consume less than 10.3. I'm not rejecting this. I'm really, really not rejecting this, according to this. Didn't we be in the ballpark a little bit better? Right? So these kind of things happen. It doesn't always fit the norm of what we expect. But you have to decide, what should you do? What would you do? What would be the first thing you would do? What would you do?
Me?
Yeah, if you got these results.
Well, if I got the equals, I would probably done the wrong way, and I probably would just kept it.
And probably do what?
I'd probably instead subtract by 1.
Well, you can't change the math of it. You still have to subtract it from 1. You still have to follow the math of it. So you realize how far off your answer is. You're the person who challenged this claim. And you realize how far off your answer is. What would you do? What would you do? Grab a new sample. Try a new sample. Sample another 100 people. But maybe the way you sampled was a little bit biased, and you didn't realize you had bias in your sample. So make sure when you sample again that you follow all the rules of finding your samples. And try it again. If you still come up this far off, maybe you're not getting it. Maybe you're saying, I'm thinking it's going to be more, but really, in fact, it's really less than 10.3 pounds per year. He's really on target with his claim. So I have to step away and say, he made a good claim. I can't challenge this. So these are things you're going to be faced with looking at. Most of your stuff fits your norm. I get it. And a lot of you were coming up with, well, why did we subtract from 1? Because it still is the area to the right. We still have to follow the rules. Good? This is a good one. Because every once in a while, one of these happens. It's a real situation. Okay, here's another one. A consumer group claims that the mean annual consumption of high fructose corn syrup by a person in the United States is 48.8 pounds. It's a lot of corn syrup in there. A random sample of 120 people gives you your mean and your standard population standard deviation. And we want to know, can we reject the claim? Therefore, what's the claim going to be, HO or HA? HO.
Oh!
So that helps us when we come here. So your claim is equal. Okay. Excuse me. So your HA, your alternative, is not equal. So that gives you the two-tail test. Were you on target with this guy? Everybody was good with this one? Did you find your z-score? What did you do for your area?
You have to
One
multiply by
minus
2.
Multiply by 2. Well, okay, Nick, if you're looking at the left-hand side, you don't have to 1 minus it.
Yeah.
Okay, so if you look at the right-hand side, yeah. But take this area, multiply it by 2.
Yeah, I got that.
Now, your decision, you rejected HO. So you came back up here, you rejected this. So we kind of didn't like this. We have to go for this one. But we can't say we didn't like, we thought it was false, we thought it wasn't true. So we have to come down here and say there is enough evidence to reject the claim. And remember what I told you, how many of you wrote the whole claim out? Good. That the mean annual consumption of high fructose corn syrup at a level of significance of 0.05 is 48.8 pounds. Good? Okay. All right. Now that you have p-value under your belts, we're going to learn another way to do this. No? Not under your belt yet? Okay. All right. So now we're going to learn another way to do this. If you bring out your notes again, we're going to jump to the part where we test the reject region.
277 or no?
I think, let me check. Is it reject region 347?
No, 370.
370. Okay, reject region. Now, not a lot changes here, except for when you make your curve. It's in your notes. It probably is the second part. We test the p-val, and then we're going to test your reject region. Let's see where it is. It's on the back of the first page. You don't have to. Yes, do that. Okay. All right, so we're going to do the same thing that we've been doing. Do you have a dealer? That's 7.1. This is 7.2. Okay, remember, when you don't have it, guys, take it out of the folder. Okay. Another method to test your hypothesis is to determine whether the z-score that you just found falls within a range of values called the reject region of your sampling distribution. A reject region of the sampling distribution is the range of values for which the null hypothesis is not probable. We're going to look for cutoff values. We're going to do the same exact thing that we just did. Left tail test, right tail test. Your p-val, we already found your z-score. We know what your p-val is. But now instead of looking for your p-val, we're going to still make a chart, and when we do your test statistic, we're going to find the cutoff critical value for that number. It'll start to make sense when we do one. We're going to do the same basically thing that we did before. We're going to determine if it's a right-tailed or left-tailed. We're going to determine what the cutoff value is, what your z value is. And if you have two tails, remember your inverse norm, divide by 2. Same thing in here. I gave you a little chart that the book uses so that you could see, and these are your most popular level of significance values, and the z-scores that we'll use for your critical values. These will be your critical values. All right, so let's see what testing with a critical value does. We're going to make a left tail test. Left tail test. Same as we did before. Shade it in. But now, instead of me giving you a p-val and you testing your level of significance, we have to find a z sub 0, a critical value, where we're going to use as a cutoff for your z value. So the first thing we're going to do is test with a level of significance of 0.01. Now, your chart is helpful once you understand where this comes from. This area is where my error is. It's the smallest error that we're going to allow, the most extreme. So we want to find out what z-score is associated with that level of significance. So if I have my area under my curve at 0.01, how do I find the z-score associated with that? Calculator, what would you do? Inverse norm. So everybody go to your calculator, inverse norm. Am I divided by 2?
Yeah. No.
No? One tail test. Keep your mean at 0, your standard deviation at 1. You're looking for a z-score. So what do we get?
2.33.
2.33. Here, guys, inverse norm.
Where is it?
Second norm.
Second norm. Oh, my calculator just was so nice. You don't need parentheses. There it goes. Okay, watch. Second bears, inverse norm. Hola. There it goes. Okay, I have to put mine in, but you don't have to do yours. 0.01, what is that? Comma. You need the 0 for your mean, the 1 for your standard deviation, and paste. Do you see your z-score? Do you see your table that I gave you? You got a positive for your 0.01. Did you do 1 minus? No, I'm not 1 minus. We're on the left-hand side. 0, 1. Do you see your table that you have in front of you? Does it say 2.33?
I think it's negative.
Because you did the 1 minus. Don't do a 1 minus. You're only looking for this tiny little bit of area. Area to the left. Now, if it was area to the right, what would it be?
1 minus 0.01
2.33. Good. So if it was over here, it would be 2.33. That's where that number in your table comes from. Okay? We did inverse norm probably a little while ago. So you guys try and find me the critical value that is associated, and I want to see your sketch, not your table. Find me for now, and we're just going to incorporate this with whatever you already did. So it's just another way to look at this. I like this way better, to be honest. Because as soon as we put it all together, it actually makes more sense. So give me a sketch, left tail, area under the curve, 0.10. Sketch, no cheating. No cheating. Do I have to do 1 minus? No. What's on the right? So, everybody should be done. Left tail test. Critical value. Cutoff. What should I get? Everybody good with that? You're not good with that? If I do a right tail test, what would it be? Positive 1.28. Good. Okay. The only other tricky one is a two-tail. Two-tail test. Now think back. Remember when we had 90%? Go back. We had 90% in the middle, and we had two tails left over. What did we have to do in inverse norm? Divide. So we first had to say 1 minus, and then we had to divide by 2. But this is the flip side of your confidence interval. This is your level of significance. So when I have 0.05, what should I do to it? Divide by 2. Good. So take this, you can do it right in your inverse norm. Before with your confidence interval, you had to do 1 minus 0.95 divided by 2, but because we have the leftover part of it already, we just have to divide it by 2. So find me, and you're going to get a negative. So we're going to get a negative and positive of the same one. Negative 1.96, did you divide it? Yeah. Okay, good. Negative, who got negative 1.64? Okay, what happened? What did you put in? How many tails do you have to share this with? 2. So what do you have to do? Divide by 2.
Right, Cheetos.
Divide by 2. Okay? Alright, let's put one all together now. Let's put it all together. You know the rest of it. Now, here's what's going to happen. This is why I like this one better. We're going to find left tail test, right tail test, two tail test. We're going to find your cutoff values. You just found it. So say, for instance, this was negative 1.96. We're going to label this reject H0. We're going to label this part fail to reject H0. So when you make your decision with your p-val, and you had to put it on your chart for your p-value, you'll no longer have to do that. You'll take it right off your graph that you just drew. So when we find your test statistic, so say you do your z-score, and you figure this all out, and your z-score comes out to be negative 1.34, we say, okay, where does negative 1.34 fall? To the left or to the right of negative 1.96? To the right. Somewhere over here, right? So, oh, what area does it fall into? Fail to reject 8-0. There's your decision. You don't have to take it out, just find the p-value. All we have to do now, instead of finding the p-value for this guy, we have to just find a cutoff and test it against your test statistic. So once we do that, we're going to compare it to that number line, and we're going to see if it falls in your reject region or in your fail to reject, H0. And the rest is the decision. You're still going to use your table, make your interpretation from your decision. The same thing's going to happen with the right tail test, two tail test. No? Question? Go ahead. You good? Alright.
So you reject the not shaded region, you reject the shaded region and not reject the unshaded region?
Yep. Yep. Because that's what's nice about this is your type 1 error is your alpha error, your level of significance. That's the part we won't allow. So that's the part we shade in. So when we hit that part, we say, oops, can't do this. We won't allow you to have it this extreme or more extreme. So now, if my z-score was negative 2.12, it's going to fall here. If I looked at this p-value would actually be smaller than whatever my area is under that curve. So we don't have to test that. We'll see right off our graph that we rejected. I like this one because it gives you your decision instantly. And after you see this happen, you'll tie together your level of significance, your area under the curve, and what's extreme and what's more extreme, hopefully. We'll see that happen in a minute. So let's try it. Again, you're going to go through the whole thing that we've been doing, state your claim, find your pieces, and all we're going to do now, instead of doing the p-value test right here, is put it on your chart, on your graph, and see where to reject or not to reject. Okay. Phew, here we go. All right. Employees at a construction and a mining company claim that the mean salary of the company's mechanical engineer is less than that of its competitors, which is $68,000. A random sample of 20 of the company's mechanical engineers have a mean salary of $66,900. Assume that your population standard deviation is 5,500 and the population is normally distributed. Why do they tell us this and sometimes they don't?
Because the random sample is 20.
Good, because your random sample is less than 30. So we know, wasn't that part of your chart? It has to say that it tells us this. Now, at a level of significance of 0.05, we want to test the employee's claim. Now, prior to this, we did your left tail test, right tail test. We found your statistic. We found the value in your curve for that statistic, and we tested against the level of significance. We're almost doing that the same, except we're not going to have to look up the value, the probability value of your test statistic. We're just going to put it on your chart. So we're going to start like this. Give me the claim. Here's your claim. Okay, less than.
So is HS.
Good. No, wait. 68,000. This is your HA, because why? No equal sign. Good. What tail test am I going to get? Left tail test. So right away I know I'm a left tail test. What's my HO? Okay. So we've got our first two things, which we always did. Go ahead.
I thought the less than goes with the equal sign.
Less than or equal to. A lot of times they say at most. At my light's flickering. At most is the less than or equal to. But not the less than. The less than is just a plain old less than sign. Okay? Alright, let's pull out your test information. You're going to sample 20 of these guys, and what's their mean? 66,900. You have a previous population standard deviation of 5,500. Your level of significance is 0.05. This is 0.05 right here. Now, we know how to find that. We know how to find your critical value. This is different. Okay. Find your critical value. We did your inverse norm. This is what we just did. Inverse norm, 0.05. Since we did this, look at your chart. If you're at 0.05 and you're a left tail test, look at your chart that I gave you. You're a left tail test, 0.05. What's your critical value? Good. This is what you just did on your calculator. Inverse norm, try it. Inverse norm, 0.05, left tail test. See if you get negative 1.645.
So for all of the previous questions, we did we've done inverse norm to find the z-score.
Not
Is
to
this
find your,
different?
this is different. We didn't find your z-score yet.
This is what is this?
Well, I'll explain it as soon as we get through this. Hang on to that thought. Okay, now, let's find your z. Same as we did before. So your x value minus your mean, and I should be negative, so I'm in the right area, and standard deviation divided by the square root of n. Let's label these regions. This guy is my reject H0, and this is my fail to reject H0. Okay. You're going to find your z-score like you always did. And let's find my z-score. But now, here's the difference. In yesterday and this week, we took your z-score, we looked it up on your table, we found your p-val. So, do that for me. Look up this z-score and find me your p-val. We're going to see if this works side by side. What do you get? Go ahead, what is it? Okay, that's fine. Now, before we took your p-val, let me test it against your level of significance. What would be our decision? It's greater than. What would be our decision if we tested p-val? Fail to reject H0. But today, we're going to do this different. We're going to take this. Instead, this time around, we found your z-score associated with this area for your level of significance, and now we're going to test z-score against z-score. Before we tested area against area. Now we're going to test z-score against z-score. So, according to this, does negative 0.89 fall to the left or to the right of negative 1.645? To the right. Here's your 0, so somewhere here. Oh, what's our decision? Fail to reject H0. Now, yeah. Side by side, watch. Here's your area. Just look up here 1 second.
They're always going to match.
Yeah, watch. They have to match. Here's your z-score. Okay? There's your area of this curve over here to the left. There's your z-score. Okay? So all we did, instead of using your areas, this time we compared your z-scores. Before we took your p-val, your probability value, the value under the curve. This time we're saying, okay, let's do it in the reverse. Instead of looking at p-vals, because p-val's more abstract for me. It's a little bit more abstract for me to try to, visualize what area it is, how big it is. Oh, this area is bigger than this one. That's why I said fail to reject. That's why we compare those. So every time you did that, you had to look at your chart. You followed it. But did you ever think that, oh, that area is bigger than that? But now, when you do it the opposite way, you actually see why you're falling into a reject HO, why you're falling into a reject HO. You actually can see it on your graph, and you don't have to stop and compare anything. But when we do this, it's a little bit more of an abstract thing. You're just taking this, lining up the zeros, figuring out why, and giving me it's less than, it's greater than, and following your chart. But this, you actually see the placement of it. If we would have put this on your chart before, on your graph, we would see this area was bigger, so we were okay. But really comparing two areas is a little bit different than comparing two z-scores and seeing where they fall. So it's the same test, we're just looking at it from different viewpoints. And just as some of you like to use a calculator, some of you don't. Some of you will like to use the reject region, some of you will like to use the p-val. If you're prone to the calculator, you will probably use the p-val because you're given your level of significance, the calculator gives you your p-val. That's a sweet test. If you use your reject region, you have to find this cutoff value. Your calculator does give you your z-score, but you'll have to find your cutoff value and draw your chart. I still need you to know how to do this one, and we'll do another one together. You can do either. They're basically the same test, aren't they? We're just either looking at areas or we're looking at z-scores. Do you guys see that? This is so important. Aaron, Damani, do you see it?
That's fair.